Hi guys, and welcome back. And it's legit, welcome back this time. I hope everybody had a really nice spring break. I hope it was relaxing, or as relaxing as it could possibly be while we're in quarantine still. I don't really have much else to say in terms of like intro-y stuff. We're just gonna kind of jump right into it. We finished transformations before spring break, so we're starting a brand new topic, brand new chapter. We're talking about perpendicular and angle bisectors, which we talked a little bit about up to this point, but we're talking about them in regards to triangles and the sides of triangles. So if anybody still looks in the textbook for any extra resources, we're talking about section 5.1. Okay? So I think we kind of have an idea on what a perpendicular bisector is in general. So talking about perpendicular bisectors in terms of sides of triangles is pretty self-explanatory, I think. A perpendicular bisector passes through the midpoint of a side and is perpendicular to that side. So if you're talking about triangle ABC here, CD, it would be the perpendicular bisector of this side AB, because D is your midpoint, and CD is perpendicular to AB. All right? So that's just kind of the idea of perpendicular bisectors in general, but these theorems are saying two different things. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So what that means is, since we just said CD is the perpendicular bisector of AB, C, the point up here, is equidistant from A and B. So what that means is AC is congruent to CB. That's what theorem 5.1 is saying. That's the perpendicular bisector theorem. I'm still not giving you any proofs. Even if we're online, like I still said, when was that? Back in January or February, that we're done with proofs for the year. That's still true. So this perpendicular bisector theorem and its converse are going to be used more so for like algebra problems. All right, so don't freak out. You're not getting proofs. And then the converse, I think, hopefully we might remember what a converse is. You just take the hypothesis and the conclusion and just switch them. So if you know that a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of a segment. So we'll talk about point E this time, down here. If you know that AE is congruent to EB, then that lets you say this segment ED is a perpendicular bisector of AB. All right? That's kind of what these are saying. So, if we're asked to find BC, well, what do we know? We have triangle ABC. We have this segment CD that is perpendicular to AB, and we have AD is congruent to DB, which means D is the midpoint of this side, so CD is the perpendicular bisector of AB, which means AC is congruent to CB. So if AC is 8.5, BC, or CB, same thing, also has to be 8.5. Really long explanation for a really simple problem, but that's it for this one. Okay. We have a triangle here, so we know that we have this line that's perpendicular to a side of a triangle, and we have WX is congruent to WZ. So we know, because of this congruence, that W is equidistant from the other 2 points in the triangle, X and Z, which means this line that goes through it, WY, is the perpendicular bisector of that side, XZ. So we can say then, we have the perpendicular piece, we can say that XY is congruent to YZ. So if we know YZ is 6, XY also has to be 6. Okay? Really, really similar to the first problem. Again, we have QS is the perpendicular bisector of PR. So the remaining two sides of this triangle are going to be congruent. PQ is equal to QR. So now that we have expressions, we're just going to set them equal to each other. And then solve. So 4 is 2x. That means x is 2. But it does say find PQ, so we are going to plug it back into this expression. Since we know they're equal, it really doesn't matter in the grand scheme of things which one you plug in or which expression you plug in for. You should get exactly the same thing no matter what. So 3 times 2 is 6 plus 1 is 7. Which, yeah, you should have gotten the same thing if you had plugged it into this expression. Okay? Okay. All right. When 3 or more lines intersect at one point, the lines are said to be concurrent. The point of concurrency is the point where all these lines intersect. So since you have 3 different sides of a triangle, you can create 3 different perpendicular bisectors. And if you create 3 different perpendicular bisectors in the same triangle, they're all going to meet at some point. And that point where they meet is called the circumcenter. All right? So there's a really interesting theorem about circumcenters. In general, what it says is the circumcenter is equidistant from the vertices of the triangle. So if P is your circumcenter, then it's the same distance away from A and C and B. So that's what it says here. PA is congruent to PB, which is congruent to PC. And all of this is still true about perpendicular bisectors from before, that PE, for example, is perpendicular to AC, AE is congruent to EC. You got a lot of stuff going on here that you can use depending on what the questions are asking you for. So, example 2 is asking for a lot. You know that DG, EG, and FG are all the perpendicular bisectors of this triangle, and it's asking you for 3 different things: GC, BE, and CE. All right, so GE is 7.3 and BG is 13.4. So because we have this piece of given information, perpendicular bisectors, we know G is the circumcenter, which means G is equidistant from all 3 vertices. So GB is congruent to GA and is congruent to GC. So if we know GB is 13.4, GC also has to be 13.4. Okay? How would we find BE then? Well, more complicated, because if you look at what's going on here, we know GB, we know GE. BE we can consider the third side of a smaller triangle within the figure. And it's a right triangle because we know that's perpendicular bisector, or because of this right here. So to find this third side of our right triangle, we can use the Pythagorean theorem. With 13.4, since it's opposite the right angle, that's going to be our hypotenuse. So 7.3 squared plus our missing leg squared, which is BE, is equal to 13.4 squared. I gotta get my calculator for this. Nope, that's not what I wanted to do. 179.56 minus 53.29. Okay, so it's about 11.2, which makes sense considering the figure. It's got to be shorter than the hypotenuse. And it looks like it's probably going to be longer than GE, which is 7.3. So we have that, and then all we need is CE. Since we know that GE is one of the perpendicular bisectors, the whole side BC is getting bisected. So BE is congruent to CE. And if we just found BE is approximately 11.2, CE is also approximately going to be 11.2. And that's that for that entire problem. Okay? All right, there's no definition for angle bisectors here because I'm pretty sure we're all okay with what an angle bisector is. It's a line that cuts an angle in half. But again, there are some theorems that are important to know about angle bisectors that sort of work similarly to perpendicular bisectors. If a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So part of what's also important about this is the fact that the shortest distance from one point, or like from a point to a line or to a line segment, creates a perpendicular. So when we talk about this distance between the sides of the angle and the angle bisector, this perpendicular is implied. All right, so this probably will show up in a lot of your pictures, but you do need to also have this idea that this distance creates that perpendicular with the actual side of the angle. All right, so if we're talking about point F on the actual angle bisector, we know it's equidistant from both of these sides. So we could say that FD is congruent to FE. That's what the actual angle bisector theorem is saying. And again, converse is just in reverse. If you have a point that is equidistant, or if you have a point on a line, what does it say? If a point in the interior of an angle is equidistant from the sides of the angle, then it is on the bisector of the angle. All right? So if you have this point on a line that's equidistant from both sides of the angle, then this point is on the angle bisector. So I think a lot of these problems are going to be very similar to the perpendicular bisector problems from earlier. Yeah, all right. We have from the diagram that ray AD is an angle bisector because of these two arc marks, which show congruence. So that means we know that BD is congruent to DC. So if DC is 5, DB also has to be 5. All right? Okay. We know point W is on a line. We know point W is on a line that is equidistant away from these points Z and X. And then also create these perpendiculars. So that means this ray, YW, is an angle bisector. All right, which means angle WYX is going to be congruent to angle WYZ. So since we know angle WYX is 28, we know angle WYZ is also going to be 28 degrees. Okay? Exactly the same thing here. All right, like from earlier. We have the angle bisector, we have this distance, we know this distance, or these distances are going to be equal. So because we're dealing with expressions now, we can set them equal to each other. I think this is going to be easier to solve. X is 3. And again, QS, we're going to plug it back in. So 4 times 3 is 12, minus 1 is 11. All right. There is also a point of concurrency for angle bisectors. If you draw all 3 angle bisectors within a triangle, they're going to intersect at this point, which is this time called the incenter. All right. And the idea now is different in terms of how the incenter relates to the entire triangle. The incenter is equidistant, not from the vertices, but from the sides this time. So what that means in terms of this picture is that PD is congruent to PE, which is congruent to PF. All right. You have to be careful of the difference between circumcenter and incenter, perpendicular bisector versus angle bisector. All right. When we still talk about distance, though, between a point and a line, it still refers to this shortest perpendicular. So we might have to use right triangles or mini right triangles within the whole figure again. But we'll see. That's still a possibility. All right. Find ST and the measure of angle SPU if S is the incenter of triangle MNP. Okay, so ST is all the way over here. So there's really not much we can do with that at this point. We can work with this over here. We know SP is 10, and we know UP is 8. We cannot say SN is also 10, and so is SM, because we're talking about angle bisectors this time, not perpendicular bisectors. But that goes into what I was saying earlier with the fact that when we talk about distance from a point to a line, it creates that perpendicular. So SUP is a right triangle, which means we can use the Pythagorean theorem to find the length of SU. It is a multiple of a triple, if you guys do remember that. It is a multiple of the 3, 4, 5 triple, so SU is going to be 6. If you don't remember your triples, you can definitely use the Pythagorean theorem to verify this. But that 6 is important because that goes into the in-center theorem that we just talked about. SU, the distance from the in-center to this side, is going to be the same from the in-center to every single side. So SU is congruent to ST, which is also congruent to SR. And ST is what we were asked for. So ST is going to be that exact same 6. All right? So what else did were we asked for? The measure of angle SPU, which is right here. Again, it's all the way over there, so we're not going to deal with it right away. We're going to deal with the other stuff. This whole idea of in-center relates to angle bisectors. So 28 refers to angle SNU. And since we know we're talking about a whole bunch of angle bisectors here, if a piece of this whole angle in the triangle is 28, the other half, and I'm saying half on purpose, also has to be 28, because again, angle bisectors. Same thing down here. If SMR is 31, since we're talking about angle bisectors, SMT also has to be 31. Which means angle N as a whole is 56. I'm just going to make a note of that. And angle M as a whole is 62. And we hopefully remember when we first started talking about triangles that the sum of all the angles in a triangle is 180. So the entirety of angle P is going to be, I need my calculator for this, 180 minus 56 minus 62. Oh, which is also 62. So, okay, that makes our lives a little bit easier because SPU is only part of it. But because we know we're talking about angle bisectors, SP, the segment, cuts the whole angle P in half. So that means angle SPU measures half of 62, which is 31. All right. And I believe, yeah, that's all I got for you in terms of section 5.1 stuff. I think by this point, I should have posted a little something about the AB day schedule that we're moving to. You guys probably should have gotten something on that already in the mail. So I'm not going to go into that too much. Just some other little things that you probably need to know in terms of AB day stuff. But same thing as usual, if you have any questions about any of this going forward, definitely reach out. I know you guys are really good at that. And yeah, I think that's everything. Talk to you guys soon.